All right, modeling radioactive decay on example 4. So whenever we have bacteria, a lot of times we talk about how long it takes to double, and with radioactive decay, a lot of times we talk about its half-life, which is how long does it take for there to be half as much.
Right.
So this says, suppose the half-life of a certain radioactive substance is 20 days, and there are 5 grams present initially. Use this information to create a model and find the time when there will be 1 gram of the substance remaining. So again, we're not actually given a percentage rate necessarily, so we can stick with the simpler form of our exponential function.
Right.
So y equals a times b to the x. A is our initial amount, which is 5.
Right.
And then we want to talk about basically the half-life.
Well, I think on half-life, it's not the game.
No, it's not the game. We're talking about what I just said earlier, that half-life is talking about how long it takes to get half of the substance.
Yeah, so not the game.
So not the game.
All right.
Yeah. So
which I hear is fun.
I haven't played it, so
I haven't either.
If we're talking about half-life, then we're talking about when will there be half as much as 5, which that would be 2.5. Okay?
Right.
And they tell us it takes 20 days for that to happen. So that means that I should put a 20 here?
Is it a 20?
That's what we need to figure out.
I think so. That's your time part.
That's my time part. Okay, so after 20, so that means that x is a number of days.
Yes.
So after 20 days, we're at 2.5. So we plug this in for x and y so that we can solve for b.
What's that 20 doing up there?
What do you mean, what's the 20 doing up there? That's where it's supposed to be. So to solve this, we divide by 5. And the way this works is because we're picking a half-life, we should always end up that this left side is a half. Like that.
Oh.
Like if we picked the right numbers, it should be a half over here. So to solve this, you may be like, I don't know how to solve that. Sure you do. It's the 20th root. Everybody knows that.
What's the 20th root of that thing?
Okay, on your calculator, there's a button. You want to type in 20 first, and then you want to press, if you're on an 84-ish, you want to press math, and then it's like the 6th or 7th option, and it should have like an X radical, and then you type in this case, the 1/2, which is 0.5. I don't know, and then conversely, 0.5.
Did you say conversely?
0.5 to the 20th root of 0.5 is 0.5 to the 1 over 20.
Yeah.
So that's another way of writing that.
On the Inspire, you also have the little caret button. If you hit Control caret, you can get a template to fill in. So all of these are.
There's lots of ways. So what does it give us?
0.9659.
0.9659. And since we're modeling, the more decimals we have, the better.
Yes,
because
indeed.
it gives us a more accurate set of information. So plugging this in as y equals 5 times 0.9659 to the x. We want to know, that is part of our answer. It asks us to create a model, but we also want to know the time when there will be 1 gram of the substance remaining. So we want to know when will 5 times 0.9659 to the x equal 1, which, like we did on the last problem, we can definitely type this in all on one side. So subtract 1, it equals 0. Graph that, and then see where it crosses the x-axis.
So graphing right now is 5 times 0.9659 to the x minus 1. Ooh, it's way over there.
Yeah, so you will have to change your X max on your window. And really, the zoom out feature or zoom fit tend to not be super helpful.
All that changes is the Y's.
Yeah, all we need is to get the X max to be bigger.
Okay, I went out to 200 on mine, and it's going to show up in there.
Yeah, it's a lot less than 200.
It's a lot less.
Hey, go big or go home.
Wow, that's a... So I got 46.382.
Okay, so that's how many days? So after a little over 46 days, we'll have 1 gram of the substance remaining. Is that okay for our answer?
I think so. I mean, it's...
The book a lot of times on problems like these will end up saying things like, oh, it's 46 days and 11 hours, which is what the book says on this one. Because they got a slightly bigger number than us. Again, this is a rounding sort of issue.
We rounded differently, so...
Yeah, so that can happen sometimes.
Yeah, you could be off just a slight skosh, but it should still be really close.
Yep.
What's next?
Oh, scientists have done something relevant.
What?
Have established that atmospheric pressure at sea level is 14.7 pounds per inches squared, and the pressure is reduced by half for each 3.6 miles above sea level. Using this information, create a model and find the altitude above sea level at which the atmospheric pressure is 4 pounds per inches squared.
Now, maybe a different way to solve this problem, which is similar to the previous one because they're both talking about half-life, is we could use a half for our base, which would then still get us to the same answer, but maybe our equation would look a little bit different.
Okay. So what do you think we should do?
So let's take the 14.7 pounds per square inch. That's our initial value because that's what it's at when we're normal.
Right.
Okay.
So that's the A.
Right.
Okay.
So we could do 14.7 times the base, which would be 1/2 in this case.
Okay. So it's kind of like when we were looking at the chart and we said, oh, each time he times it by a half. Okay.
But now on the previous problem, we used X as our power for years instead of saying ever number of days.
Yeah.
But on this one, we could actually have a fraction for our distance above the what you call it,
I don't know what you're talking about right now.
The altitude. The altitude.
Altitude.
Yes, because every time you go up 3.6 miles, we've lost half. So we could have this situation where we have X over 3.6.
Right. And so what's happening there is basically...
Once you move 3.6 miles, you lose half of your stuff.
Okay. And so if we wanted to, we could rewrite this model up here that we got, for example, 4, right? And we could say that 5 is our initial value.
Right.
And 1/2...
Right.
We're losing 1/2, but we're losing it every 20 days.
So after you go through the whole 20 days, that's 1/2.
Okay.
Yeah, just tossing it out there.
And that's
different ways to solve the same problem.
Yeah, and that's kind of easier, actually, in a lot of ways to do it that way. So where you need to use this information to create a model and find the altitude above sea level at which the atmospheric pressure is 4 pounds per inches. So
well, that's the Y part then.
4 here.
So
let's solve this.
So a little solvey Roonies here.
We'd get everything on one side and graph it to see where it goes through the x-axis. So
-4.
This right here is what we're typing into
I kept the same window as the previous problem, which was out to 200, and that worked fine.
Yeah, it's nowhere near 200.
It won't be, because that would be really weird. But I'm going to get a number between 0 and 10, and the number I get is 6.75988. 6.75988. And that is the distance above sea level at which our atmospheric pressure will be 4 pounds per inch squared.
So is that inches?
I believe that is miles. Mrs. K. Steve 320.
Okay, so that's our answer
There you go.
And there will be a problem in your assignment that refers back to this, that you want to keep in mind this model that we came up with, or this information, whichever. This information is what it uses whenever you have a problem that has atmospheric pressure.
Right.
So.
Right.